De-anonymization of mobility trajectories, dissecting the gap between theory and practice. Due to the high research and business value, anonymized trajectories has been collected by the Internet Service Provider, that is ISPs. Due to the high risk, for ISPs, there are strong motivations to monetize or share the anonymized trajectory data, leading to a growing privacy concern. Here, the key problem is that how likely users can be de-anonymized in such ISP shared trajectory data. To answer this question, early studies have evaluated the theoretical bound, privacy bound of the dataset by accessing the uniqueness of trajectories. They show an appealing result. That is, 4 location points are sufficient to uniquely identify over 95% trajectories. The problem is that true in practice? However, practical de-anonymization attack is also challenged due to the lack of large-scale ground truth dataset. Early studies have to settle on small-scale dataset or simulate their attack on the synthesized dataset. For example, a work in 2011 sample part of the same dataset as the external information and victim dataset. We stressed this problem by collecting three real-world ground truth datasets. We see that we have ground truths due to this dataset are collected from the same set of users. Specifically, the victim dataset is an ISP trajectory dataset, which is obtained by collaborating with one of the largest internet service providers in China. Users access logs to cellular towers from April 19th to April 26th, 2016, covering the whole area of Shanghai, are involved in this dataset, which can be transformed to their location trajectories. On the other hand, we also collect the 2 online social network datasets as external information, including Weibo, which is one of the largest social networks in China, and Dianping, which can be regarded as Chinese Europe. As we can observe, we have over 2 million ISP trajectory and over 40,000 external trajectory in each online social network. The large-scale dataset guarantee helps to solve the critical problem of leaking ground truth dataset in existing works. Then, as for how we obtain this ground truth. In fact, we obtain this ground truth by examining the HTTP traffic. Based on the ISP traces we have, we found that mobile apps of Weibo use HTTP protocols to communicate with their servers. Well, the user's ID of Weibo are visible in the HTTP request. Thus, we can obtain the user's online published check-ins and users uploaded GPS locations of the same set of users by matching their IDs. Similarly, we also obtained the user's uploaded GPS location of Dianping in this way. We are aware of the privacy implication of using such dataset and have taken active steps to protect the privacy of involved users. We got ethical approval from Weibo and Dianping. For details, please see our paper. Then, here comes to the thresh model. Before ISP published the anonymized dataset, before ISP published the trajectory dataset, he replaced each user identity with a pseudonym. Then, for the adversary, the target is to match the anonymized traces with the external traces. For example, Weibo's Dianping's traces. Due to the social network has user identifiable information. In this way, we can map the real-world identifier to the anonymized traces. Here is a very quick example. For each pair of external trajectory and its candidate anonymized trajectories, adversary define a similarity function and measure their similarities. Then, based on these similarities, adversary ranks all the candidates' trajectories. The attack performance is to see whether the true matched trajectory is ranked in the top of the result. we use a standard matrix to measure the theoretical bound of the data set. That is the uniqueness of trajectories. Its idea is based on the key anonymity. Is it to measure the number of points sufficient to uniquely identify a trajectory? If a particular trajectory is unique in the data set, we can say that with some external knowledge, we can uniquely identify it. However, if for trajectories, if there are many similar traces in the data set, the re-identification becomes more difficult. We can observe from the result that is, with 5 random select points, over 75% trajectories are uniquely identified. The high theoretical bound indicates the high potential risk of trajectories to be de-anonymized. Then, in order to evaluate the actual performance of the attack, we implement 7 state-of-the-art algorithms, including 3 major categories. They mainly match trajectory based on their in-county event, or individual users' mobility patterns, or they are designed to tolerate spatial or temporal mismatches. We use the hit position as the metric, that is, to see the position of the first candidate, but also consider the correctness of the second, third candidates. We can observe from the results that the maximum hit position of the existing algorithms are less than 25%, which is far from the privacy bound. So, what are the reasons behind the underperformance of these algorithms? To answer this question, let us take a close look at the result. We can observe that 2 algorithms with the best performance are the Netflix and the mean square. The first use the minimum time gap between users' visits to the same locations as the similarity function. The other one uses the mean square root of trajectories, mean square root of distance of trajectories as the similarity functions. They can tolerate the temporal mismatch and the spatial mismatch respectively, and they have the best performance. Inspired by this observation, we turn to measure and understand the location and time mismatch of the same user in different data sets. We first fix the time, that is, find 2 records of belonging to the same user in 2 different data sets and in the same time bins, and see how far their locations are. Results show that over 40 records are 2 kilometers far away, which is a pretty long distance. On the other hand, we also fix the location, that is, find 2 records belonging to the same user in 2 different data sets and visiting the same locations, and to see whether their time are very different. We can observe that over 30% records are 1 hour far away. Results show that there exist significant time and location mismatches between trajectories in data set of the same user in different data sets. There are a number of potential reasons can lead to such mismatches. The first is the GPS error. For example, there are many GPS unreachable locations, such as indoor or underground. The lazy GPS updating mechanism of cell phones to save their power can also lead to the GPS errors. The second reason is the deployment of the base station. For example, a low density of base station will lead to larger mismatches of ISP trajectory with external information. The mismatches also come from users' behavior. According to a recent measurement study, over 39% check-ins on Foursquare are remote or fake check-ins. Users often generate fake check-ins to earn virtual reward or compete with their friend. Then let us return to the result of the performance. We can observe that the sparse location record also lead to the worst performance. However, we also show the distribution of the number of records per user and the number of distinct locations visited by each user in the top figures. We can observe that the vast majority of users have very, very sparse location record. This data sparsity will lead to rare encounter events and also lead to inaccurate mobility modeling, which existing methods are based on. Thus, it's also the important problem. It's also an important problem of their underperformance. So, can we bridge these gaps? Based on the above observations and insight, we proposed our method to overcome these practical problems. Basically, we define a similarity based on the conditional probability. We show the dependency of variable in our method in the figure, where node with blue color indicates the trajectory S, while node with purple color indicates another trajectory L. We consider four major practical factors as follows. The first is the spatial-temporal mismatches. To describe it, we use a Gaussian mixture model to model the spatial-temporal mismatches between the trajectory S and L. The parameters in this model can be learned from the empirical value. Later, we will also show that these parameters are transferable. Then we also use the Markov model to describe the mobility of the trajectories. Users' locations in time bins without any record can be estimated by this Markov model, solves the rare encounter event caused by the data sparsity. Third, we also consider the user location, the location context. We use the aggregated user behavior at locations to infer individual users' location transition probability more accurately, especially for these users with sparse trajectories. First, we use the time context as shown in the figure. Trajectories of the same user in different datasets usually have same active and inactive time bins. Well, method in previous method mainly focus on the values in the active time bins, but they ignore the inactive time bins. The inactive time bins are also important reason and helpful in the match trajectories. Thus, we also add the probability of this part to our similarity functions. The evaluation of performance of our proposed algorithm are as follows. We compared with our algorithm with the 7 state-of-art algorithms. The curve with black and purple colors are of our algorithms. We can observe that they outperform existing algorithms with the maximum, with the performance gain over 70%. On the other hand, we also show that parameters learned from the Weibo dataset are also helpful in the de-anonymization based on Dianping dataset. In conclusion, we collect 3 large-scale ground truth datasets, which involving over 2 million ISP trajectory and 2 different online social network, 2 different types of external informations. Based on this dataset, we demonstrate there exists the gap between the theory and practice in the de-anonymization attack. The theory bound is high, but the actual performance is low. Finally, we proposed our method to bridge these gaps by addressing a number of practical factors, including the spatial-temporal mismatches, data sparsity, and location time context. Results show that our method improves the performance, which confirm our observations. That's all. Thank you. I'm happy to take questions.
Good. We have time for several questions. Ben?
Hi. Really interesting work. I like it. So quick question. You talked about sort of some of the sparsity problems and different characteristics that made existing algorithms fail. Are there approaches where you can basically augment the data to address some of these needs, basically cover traffic?
Methods addressing what?
Yeah, just add fake check-ins or add non-existent trajectories. I understand there will be constraints on how much of that you can do, but in the context of anonymity, perhaps some of those would be okay, to add a little bit of noise and just randomize data to try to improve the sparsity and address some of those issues. Would that help?
You said about the noise. The noise is important factors in the maybe can influence the result of the performance. But existing method mainly do not concentrate much about the data sparsity. They just fill out the data with the low quality away.
Okay. Okay.
Maybe you can slightly rephrase Ben's question as thinking about the performance of your algorithm in face of different types of obfuscation mechanisms. So there are many defense mechanisms that inject some fake links in a graph, delete some real links to achieve different types of privacy objectives. So the question that comes to mind is what is the performance of your algorithm when those types of obfuscation mechanisms are applied?
The mechanism we used is the hit position and the uniqueness. They just reflect the privacy bound and actual performance in a way. But we use it due to they are the most standard metrics and can reflect the most common result. But investigate the performance of our algorithm in other mechanisms is also an important problem. Which maybe investigate in the future.
Okay, thanks. Any other questions for the speaker? Okay, let's thank Huandong once again.